where he leads the Mobile Intelligence Lab. And without further ado, Paul, the room is yours.
Thanks, guys. Thanks for the invitation. I need to say this was planned to happen at the end of last year, and there were, everything was kind of a hellfire for NetAI, and it was like the first time I had to send an email say, guys, can't do it. Can you just postpone? Which I never did, like, ever before. So this time around, despite Mobile World Congress happening, I said, okay, I'm going to set some time aside so we can speak a little bit about what we do. So maybe let me start by just kind of giving a bit of context with what's the story with NetAI. I mean, some of you know, but others don't. And this is kind of overlapping with what I'm going to present today. So we started this line of research at the intersection of mobile networking and artificial intelligence about 5 years ago. It was a strange time. People, I think we had a first paper we submitted to MobiHawk actually. It ended up in I think we tried IMC. So we were looking at long-term mobile traffic forecasting using some spatiotemporal neural networks. And the feedback was so brutal, like there's too much machine learning here. This community doesn't need machine learning. So it's a bit of a, it was a bit of a scare. And then 2 years later, like everybody was just raging about AI. And we realized one problem was that many people were just kind of taking out of the box libraries from Python and just throwing them at some problems in the networking domain where actually you could have solved them with much simpler tools. So to some extent, we built this early days expertise and we were a bit ahead of the curve. And one of the things we were doing, and because there was so much hype around network slicing, was to think about, if you have a sliced network, how do you dimension it in real time? Like, what's the amount of compute and capacity resources you need? So for that, you need to have visibility inside, what happens in the network at the service by service level. So then we came up with this idea about traffic decomposition, and that's part of the stuff I'm going to talk about today. So what we did, so actually I need to be grateful to the community here because we tried to publish a paper first and it was bashed repeatedly. And then we thought, hang on, actually I was having a chat over a beer with a friend of mine who is now a co-founder, and he has more kind of commercial background. And he said, hey, hang on, you should patent this, don't publish. So we patented, we spun out the company, and then basically all this know-how that we accumulated over the years kind of moved into what is now NetAI. So a lot of the stuff kind of builds on these, years of research, and now it kind of takes a more commercial angle. So it's more about like, how do you deploy things in practice? How do you integrate with these different system architectures? So if we have time at the end, I'll give you a brief example of, for instance, how we plug a neural network model into an open run architecture, for instance. Okay, so let's just jump straight into it if we want to cover everything. So, I mean, I guess, I kind of already sort of, hand waved at the context. So you're seeing, basically, you're looking at a mobile traffic ecosystem that is increasingly complex. You have 25% year-to-year increase in the volume of mobile traffic and a proliferation of new services and applications and devices. And each of these have very distinct performance requirements. So you need low latency for, automotive IoT, or you need reliability for industrial automation and so on. So the question is, how do you manage all these requirements in real time? So for that, you need to have knowledge, timely and predictive knowledge of what the network usage is on a service by service level, both to be able to manage networks, but once you start thinking about, building things in a sort of virtualized fashion, how to monetize those networks. And this is kind of a bit of a paradigm shift now. So you have, you can already deploy stuff, you can deploy network functions in the cloud and so on. But if you look at how things have been happening historically, infrastructure was basically driven by some estimates that you obtained with some very expensive tools like deep packet inspection, which have a scalability problem. Not that they're just expensive, but you basically every time you have a new application, new type of traffic, these are hardware probes, you need to throw them away. If it's software, you need to update like a very hefty set of rules and so on. And or you and you sample, because if it's software, it slows down the traffic, so you don't look at every packet. So you sample and you might miss things. So you have inaccurate estimates. So then you get sort of this, let's say, statistical measurements of the different types of traffic, for instance, and then you say, okay, I know what averages and peaks are, and I drive resource allocation based on that. So you don't really do it in real time. So planning is kind of an exercise that happens at best on a day-by-day basis. It's often with much kind of coarser granularity. So in essence, the information is kind of too late to be useful. So you cannot really kind of, use, even if you move now stuff into software and you have the ability to kind of, take down containers or VMs and bring them up, because you're still using this old paradigm, you're not making really the most of these new features, which allows you to have kind of more agility. And then, as I said also at the beginning, like you have a bit of kind of traction now in terms of different players started to look at how to employ different machine learning models, especially those that mine some temporal information. And we've been seeing a bunch of players, I guess we can consider now from the perspective of NetAI as potential competitors. Again, it's mostly kind of out of the box, standardized models that you train for every single location, say for every antenna. So that's a big scalability problem, and they don't really have that great performance actually. And then on top of that, the question is like, how do you monitor your network? So things are still happening, as you see on the picture on the right-hand side here. So you have people behind dashboards. You have some alarms that are triggered by, every time a threshold has been exceeded or not. So you don't have that sensitivity, and you don't have the ability to kind of configure things on a sort of region by region basis or device by device basis. So, we need all these things, but we're kind of miles away, which kind of created an opportunity for us. But at the moment, before that opportunity is going to materialize, there are some immediate consequences. So operators have invested quite a lot of money into deploying 5G, but the return of investment is really poor. And that's because there was a survey that TM Forum did with top 20, I think, operators worldwide, and they said basically, operating costs are amounting to over 65% of the total revenues. They spend a lot of time on energy and specialized stuff. So these are big expenses. And if you take, for instance, big players like Vodafone, for instance, publish yearly annual reports. And based on that, there are also some analysts that look at how the company has performed over a number of years. So what you see with a lot of the big players, their profits annually have been flat for a very large period of time, and that's on the one hand because of those costs that basically mean every time I have new demand, I meet that demand by deploying more and more infrastructure. So I'm not really smart about it, but at the same time, my customers are increasingly unhappy. So I'll give an example. I came home one night, wanted to work remotely. My broadband was dead. Pick up the phone, called my provider, say, yeah, we can send an engineer to your home in 1 week. And I said, I can't wait 1 week, man. I have calls the whole day tomorrow. Well, we can try to send somebody today at noon. So, well, because I have no connectivity, I need to go and work remotely. So you cannot send somebody. So there was like this really, weird situation whereby I thought, okay, unless they send somebody straight up, I'm thinking about moving, which is churn. Yeah. So this can happen. A lot of people get unhappy because of the service is poor, especially if they're enterprise customers, and move on. And sadly, this is a first world problem because 45% of the world's population still has no connection to the internet, which is a bit sad. Yeah. So, we made all this progress. We have 5G, but then the coverage is so. Now we're thinking about, having connected cars and, immersive applications, remote performances and so on. I mean, this is still of the realm of science fiction, sadly, because we still don't have networks that can support these new paradigms. Things will change. So, I mean, on a positive note, things will change, and I think AI will play a big part now because, you know, you look at, for instance, AT&T already has over 75% of their core network functions virtualized. You have a growing adoption of kind of cloud-based services. Vodafone, for instance, has a lot of their network functions moved into the cloud as well. And then, you know, you have people in Asia bragging about having fully cloud-native, open run mobile networks. I mean, I would take that with a grain of salt because O-RAN is still being standardized. But, you know, everybody recognizes that this flexibility allows new opportunities for reducing CapEx, OpEx, total cost of ownership. But now the network is complex and you need, you know, powerful tools. So it's just a question of time. It's not like it will happen. I think it will happen for sure. So AI will play a big part here in the management of these mobile networks, which kind of, you know, brings us to some of the stuff we are doing to kind of address this need. So I said, I guess twice already, you can't just like take a model out of a Python library and throw it at a problem and expect it to work. You need to kind of apply some domain knowledge and build neural networks that actually, you know, capture what's specific to mobile traffic, which, for instance, is these spatiotemporal correlations that are kind of unique there. So with that in mind, we started thinking about what different sort of neural structure we can combine to tackle some of these problems. And mobile traffic decomposition was one of the first things we were looking at. So this is kind of like, I want to understand what services run through a network without doing DPI, without doing kind of very complex computation. Some of the traffic is encrypted. I don't want to use very expensive tools, and I want to be able to do this in real time and not be, you know, creepy and look at what individual users are doing. So the idea here is that basically you just want to look at aggregate information about aggregate traffic. So this is stuff you can obtain from this management plane. So these are basically packet counters or like traffic counters that you can collect from various network elements, and they tell you, okay, over the past 5 minutes, this is how much traffic I have been seeing. That can be at the level of antenna. And then you want to break that into the different services that make up those aggregates. And maybe you want to do this at the level of a set of base stations. Maybe you're running like a mobile edge compute facility that manages a couple of cells, and you want to do that at that level of, you want to do it at the level of, let's say, an urban region because you have a data center that serves a bunch of applications in a particular way. So you're instantiating some network function just for that locality. So the idea here, as I said, is, you know, in doing that decomposition, we're aiming to exploit these spatial-temporal correlations that are unique to mobile traffic. So this is stuff we patented, and also, I mean, we had a paper at Mobicom about this in 2020. So I'll talk about this in a bit more depth. What are the challenges of doing decomposition and so on a bit? I mean, just kind of off the top of it, if you think about it, if you take any of this, you know, signal, you know, you can decompose that into kind of an infinite numbers of sums that will lead to that. So you want to be able to do decomposition that is unique and correct. Yeah. You want to make sure that, you know, whatever you decompose it into reflects what actually happens in the network. And that's what you kind of learn during training. So how do we do that with microscopes? So, I mean, you have a deployment, which is typically a point cloud. And you can, for instance, use like convolutional neural nets on input that is not in a matrix form. So the first thing is how to basically make that data amenable to any, you know, convolution, for instance. And in the second part of the talk, I'll show that actually now we know how to do this without using traditional convolution. We came up with an operator that actually can work directly onto point clouds. I mean, to some extent, we've been sneaky here because I think the image processing community has been working with such tools prior. And we were able to kind of understand what are the benefits and try to adapt them to the domain. Yeah. Because if you look at it, what happens here, once I do the mapping, what do I see here? I have the aggregate traffic snapshots across multiple time instances. So this is almost like a 3D image, right? So every location you can see, this is the intensity of the aggregate traffic, but you can think about this like if it was a pixel, it would be, you know, the intensity of that pixel, okay? And then if it's over time, it's almost like a sequence of frames. It's almost like a video, right? So you take these sort of traffic snapshots and then you put them through a neural network, and I'll talk about that. And then there's a question of how you train that neural network in a sensible way. And then at the output, you want to basically transform these aggregate traffic snapshots into snapshots of the, you know, volume of traffic for all the services that are of interest. The beauty of the pipeline is that you're not really restricted to what neural network you want to use. So depending on, you know, the use case and if there are any sort of complexity, accuracy trade-offs that you need to achieve, you can opt for a simpler neural network that is faster to train and compromises maybe a bit of accuracy, but maybe that's okay if you, let's say, do allocations every hour or so. So let's start with the first step, which is kind of important. So the idea is how to convert these traffic measurements into something that is suitable for analyzing with neural networks without distorting any geographic information. And that's important because if you could do a one-to-one mapping, you know, just take a grid and move every point in the cloud to a point on the grid, done. The problem then is if you do that in a naive way, you're losing that spatial information. So you're losing some of these correlations, which then allow you to kind of make inference with high accuracy. So you want to kind of, you know, minimize that displacement. So the way we do this is using this kind of, it's an old tool called the Hungarian algorithm. So idea is you build that grid, that regular grid, which has the same number of points as the number of antennas you had at the beginning. So now if I had the input on such a grid, I could do convolution on this. And then to do the mapping, basically we do this one-to-one association. And the idea behind Hungarian is that you're doing this association while trying to minimize the average displacement between the original location of the points and the points on that grid that you basically want to use for further processing. And the beauty of the Hungarian here is that you run it once. So, I mean, assuming that your deployment doesn't change, I mean, maybe if we have time at the end, we can talk about this. I mean, operators continue to evolve their network. So this is a challenge. You might have to kind of do this processing periodically if you add, let's say, new antennas in the network. But the benefit is that, you know, whatever you do decomposition at deployment scale, for instance. So you don't need to train it for every element. And also you do this pre-processing once, and that's something that you run in polynomial time. So it's kind of nice. So you've done this pre-processing, you have the aggregate traffic snapshot. So now basically you can insert some neural network that learns what are basically the different spatial temporal correlations in order to solve that decomposition problem. So kind of, you know, what features can I learn to be able to do a mapping from aggregates to snapshot of decomposed services that correspond to these aggregates. So you could use, I mean, a CNN, an LSTM, whatever you want. What we came up with here is kind of a brand new class of neural networks, which we called 3D deformable neural nets, or 3D def CNN. So idea here is basically you take inputs which are all these three-dimensional tensors of aggregate traffic. So I look at the intensity of traffic at different locations across a historical window, let's say past 2 hours. And I give this to these 3D convolutional blocks, and I'll explain how these work. So this will give me some abstract features, which then I will basically pass through this we call these zipper convolutional blocks, and this is something we used prior to traffic super resolution, which was basically looking at coarse geographic aggregates, and we wanted to understand what happened at a sort of a fine granular level. So this is kind of similar to a ResNet. You're building an ensemble system, and you're trying to basically use those to provide another set of features that later on you will decode with some convolutional blocks into service-wise traffic snapshots. So how does 3D convolutional neural network operation work? So basically, if you look at the convolution, you have a filter which is rectangular, and you kind of scan an input with that, and so on. In 3D convolution, you have a filter which is a cube, and you scan the input map, which is a bigger cube, space and time. Now, what we do first, we learn some offsets to be applied to that filter. And this will basically define what's the degree of spatial-temporal correlation between different locations in the input. So with that, we basically deform that filter. So the filter is no longer compact, but it basically learns when I slide it across an input, what are the locations that present more correlations among themselves. And with that, I will obtain some set of abstract features that later on I use with the zipper blocks to kind of translate into these sort of snapshots of what happens at the individual service level. So that's something that you learn during training, and then you basically build an output map, which is something that again, it's something abstract that will correspond to different services. And then as I said, depending on what you want to do. So, if you don't care so much about accuracy, and this is a structure that takes quite a bit of time to train, and you want to train quickly, you can say, okay, I'm going to use it like a vanilla LSTM, and I keep the same pipeline. The other question is like, what kind of loss function or other sort of post-processing I should do in terms of like making sure that the output makes sense. So for instance, I decompose an aggregate into multiple services. I want to make sure that those services sum up to the original aggregate, right? That's to do with output normalization. But the question is, when I train, what kind of loss function should I be using to train? And I'll show some results, and you will see that actually it does make a difference what kind of loss function you choose to train those models in terms of the performance of your inference. Okay, so that's what you're going to obtain at the end, the estimation of the services that are of interest. So here what you see is basically how well I perform. I'm going to spend a bit more time on talk about the data set we use here in the second part. It's the same data set. We had the data set from a large operator collected over the span of 3 months, over 700 antennas, over 30 services. And here we wanted to see how basically if I do decomposition with a bunch of say different sort of loss functions, what's the best performing one? It's funny, I have some labels missing here. So every group of bars should correspond to a different network, and then every color corresponds to a different loss function. And obviously, you will see that this should be the 3D deformable CNN, and you'll see that if I train with a cross entropy, that's the best performing one. So yeah, it's funny that these things disappeared. So here we looked at an MLP, a CNN, vanilla LSTM, a deformable convolutional neural network, which is 2D, which people use previously for sort of semantic segmentation in imaging and so on. So it's kind of a bunch of benchmarks. Surprised that we can't see them labeled here. Of course, I mean, key takeaway is that, what we've done is working best. And then there was a question like, okay, so you evaluate errors. So you want to make sure that, whatever you predict is kind of as close as possible to the ground truth. So if you have a test set and you did decomposition, you want to make sure that the output of that decomposition is as close as possible to the ground truth in that test set. So we computed mean absolute error and normalized mean absolute error. So this is basically kind of, okay, the error might mean, I have, I don't know, 15 megabytes of error. Okay, so what does that really mean? Like what's the magnitude of that with respect to the volume of traffic for one specific service? So that's why we started to look at basically how that error, looks like on a service by service basis. So if we normalize by kind of, the maximum traffic here, and this is kind of why you have the other y-axis. So key takeaway here is that basically you have a normalized mean absolute error which is below 1.2%, which is pretty good. I mean, most of the time, you're predicting with quite high accuracy. So I'll show you an example. So this is at the level of a data center, I think. So you take a traffic aggregate as an input. This is normalized. So you want to split that into a bunch of services. Here I'm showing 3 out of 30. So Spotify, Facebook, and Snapchat. And we took Spotify because this is kind of quite spiky. So you download a song, you play it, and then it's kind of quiet. So you'll have all these kind of high spikes, which are notoriously hard to predict. And you can see, I mean, in situations like this, we capture the trend quite well. The spikes are hard to sort of, infer. But since we've done this work, we've been working on a bunch of other things where basically we try to capture that, because that, to some degree, that's uncertainty. So then the question is, what do you do to kind of, have forecasts that are not a single point, but they are, for instance, a confidence band that gives you sort of a better understanding of in what range I expect a signal to be. I think I'm doing fine with time. So if there are questions up to this point, I'm happy to pause a little bit before I move on to the next part. I take the silence as a no. Okay, cool. So in the second part, I'm going to talk about a dynamic convolutional operator. So you recall I said, hey, look, you have a set of antennas. I want to, for instance, do forecasting. So I'm done with decomposition. Now I have the information about what happens at the individual services. But I want to predict how they would evolve. Why? Because it takes a bit of time to, power up a VM, for instance. So I want to have that information ahead of time. Or if it's like I want to take down or power up a couple of carriers at the level of the radio access network, that's even kind of more time consuming. So I want to have this information well ahead of time. So forecasting starts to make sense. Now, antennas, I can basically, translate the information that comes from these as these geospatial point clouds, and I need to forecast on them. And you remember we were doing Hungarian, which is not necessarily ideal, especially if, let's say, you deploy new places, or let's say, you have some events where you have sort of mobile deployments. Yeah. So you have power, which is on like all this idea of like network on wheels. So you start moving the antenna depending on where the demand is moving. That typically happens, for instance, when you have events. So, of course, I mean, if everything was grid, then of course I would like to extract all sorts of spatial temporal correlations, and I could do spatial with CNN type structure, and I could do temporal with LSTM type structure, which is basically this kind of recurring neural networks. But then, that's rarely the case, as we said. So you typically do some mapping, yeah. And even with Hungarian, recall, I mean, we do mapping from a point cloud to a grid, and I try to do this with minimal displacement, but there still is some displacement, and this introduces some distortions, and that can harm the accuracy of whatever I forecast. So what we wanted to do is say, hey, look, I mean, can we forecast straight onto these point clouds, even if let's say they potentially move? So we said, well, actually, that would be nice, but there are no like immediate models we could use. Some things have changed since then, and actually, as we kind of kept working on this, new benchmarks appeared, and we started comparing against them. I think there's kind of a lot of credit to be given here to the imaging community, because they were looking at this from kind of a image classification perspective. But I'll come back to that. So what's the idea here? So I have an input, as you see here on the left-hand side. So for every point, I define some value features. So that can be, let's say, the volume of traffic for different services that I observe at that location. And then I have some coordinate features, which is basically, what's the position in the deployment of a network element where I want to do forecasting. And then for each point in that input, with this dynamic point convolution, what I do, I basically compute some weighted summation over its neighbors. Yeah, so there's a question of like how many neighbors I should select and so on, and then I will basically obtain an output and move on from there. So here, basically, the way I compute things is with different weights, and this is something that you learn during training. You see all sorts of weights, like, okay, how much weight should I give to the nearest neighbors next to me? So here's an example with 5. I'm looking at them and I'm doing some summation with them, and then I give them different weights. And that's something that you basically learn during training. So then with this, I mean, we basically build this deconv operator, and we kind of transfer, I mean, with that, we sort of replaced what you have in a traditional sort of LSTM cell. So you have basically a cloud LSTM. So you basically replace the traditional convolution, which is here, that's why the arrow, with this dynamic convolutional operator. And the rest are kind of the same. You have state, hidden state, a memory cell, and so on. Then you have a forget gate, an input gate, the output gate, and so on. Yeah. And then you will stack some of these. So in our case, we basically took this sort of sequence to sequence learning approach. And in this example also with some attention. Yeah. So we build this cloud sequence to sequence cloud LSTM with attention. So idea here is like you have a sort of an encoder decoder architecture. So in the decoder, you have a stack of these cloud LSTM blocks. You take the input. So you take basically snapshots of traffic at different locations, let's say over M snapshots. You build some embeddings, you pass them through a stack of cloud LSTMs. You have these abstract representations, and then you give them to a decoder. And all these dotted lines that you see here, these are the tensions. So you want to be able to visit different locations in the input at any point in time. So you want to kind of understand, this is what some people are doing in the NLP community. So, some parts of the input might have more influence of the final output than others. So then the decoder basically translates these abstract features that have been encoded into other features that are passed back to another stack of cloud CNNs, then which basically kind of output the forecasted values of the input over, let's say, J time steps. This is basically the output of that neural network. So this is some work we ended up publishing at AAAI in 2021. So I said I'm going to mention the data set a bit more here, and then I'll speak a little bit about the results as well. And then I think we'll have a bit of time to give you like a taster of how some of this stuff can be deployed in practice. So then again, I mean, here we use actually 2 data sets for 2 different cities, in 2 large European cities. This was all about 3 months of data, over 700 antennas. Aggregation level was every 5 minutes. And we had over 30 different services, including YouTube, Netflix, Instagram, so on. So we take input, which is 1 hour, 12 snapshots, and then forecast in the following 1 hour, 12 snapshots. in most of the cases, but we sometimes do only half an hour, 6-step prediction. And then we also look at what happened long term. Let's say I want to do 36-hour forecast, so I want to know what happens in the next 3 hours. Yeah. So then there was a question here, like, okay, how do I compare things? How do I kind of benchmark this? So we looked at a couple of other things, and I said, I mean, lots of credits to the image kind of processing community. So they had this structure called point CNN. So here is basically the idea, kind of perform convolution over point cloud, but there's no kind of, recurrent elements. So it's not like something that you would use for forecasting. So this is something that people have been using for image classification to understand, whether there are any specific features that allow you to better classify what's happening in an image. Then we use conv-LSTM, which to some extent is something we extend here. So this is sort of state of the art now in spatial temporal predictive learning. And then there were a bunch of benchmarks we devised based on the cloud LSTM. There's this cloud CNN, where basically we take the operator that we proposed, we stack multiple of these, and then we came up with another structure which we called point LSTM. So here the idea is that you replace the cells in conv-LSTM with this side convolutional operator that is being employed in this point CNN for image processing. There's been some work done on graph neural nets, which is kind of relevant here. So there is this work on spatial temporal graph neural nets, where basically you do convolution, but basically you do mapping of the point clouds onto some graphs, and then you do that based on the distance between the different locations on a graph. I mean, since we've done this work, actually, we've done quite a bit of work in that direction, and we have some newer models where we use some even cleverer graph neural networks to simplify the training process and maintain the same performance in terms of prediction accuracy. But we don't have time for that today. And then there was another benchmark we were looking at, which is this, I guess this is state of the art in terms of this spatial temporal forecasting on grid structural data. So you do the pre-processing, you put everything on a grid, almost like an image, and then have a sequence of images and so on, and you do this spread RNN++. And then we used a deformable CNN as well, which is kind of similar to what we had in the previous part of the talk. So you don't have a compact filter, but you learn the shape. And then we had a bunch of other variants we considered to our cloud LSTM. So we did a kind of cloud with RNN, which is simpler, and cloud with a gated recurring unit, which is another form of kind of temporal neural network model. Then for the sake of completeness, we also look at some traditional things such as MLP, CNN, LSTM. So I could show you some boring tables, which I thought it's a bit, daunting. So I thought maybe I just highlight kind of key results here. So how do you quantify the performance of a forecasting tool? So you look at previously similar to what we did with microscope. You look at mean absolute error. You look, for instance, at the root mean square error, which again is to some extent similar to mean absolute error. But then there are a couple of other things which people have been using in the kind of a single processing domain, like peak single to noise ratio or structural similarity, where basically you want to see how much the output differs from the real input, the ground truth, stuff like that. So we did that across all the approaches, and then for the numbers I'm reporting here, these are 6-step predictions, so half an hour forecasting window. And then, key takeaways here, like you have, depending on the model you're looking at as benchmark, you have up to 46 lower prediction errors, which is pretty good. Long-term forecasting is stable. So we looked at what happens up to 36 steps. So imagine now your reporting granularity is half an hour, 36 steps, it's quite significant. So you can predict, for a good chunk of time. It doesn't come for free. This is important. So there is a cost. So the training time is about up to 21% longer than looking at the vanilla conv LSTM. So that's the price that you pay for this increased accuracy. But on the upside is that you don't need to do any mapping, so you don't have this pre-processing cost. And this is, as I said at the beginning, particularly important when the shape of the deployment changes or some of these elements that at the level of which you want to predict change their location, so they're not fixed. Cool. So let me spend maybe just 5 minutes and just kind of show you how you could deploy some of this stuff in practice. And this is something we are doing with NetAI. So I mean, we embarked quite heavily now on this ORAN journey. So here we're working actually quite closely with VMware. So VMware have developed this run intelligent controller rig, and they have a real-time version and a near real-time, non-real-time and a near real-time version. So the near real-time version basically you should be able to kind of provide output within tens to hundreds of milliseconds. I mean, in our case, we can do inference and city scale within less than a second. So if you partition that input at the level of a centralized unit or a CU, then you can reduce that time because you're not going to manage hundreds of antennas at the level of a single CU. So the idea here is that basically you have the XUp that interfaces with, there's a shared data layer. So here is basically where you would get the aggregate data. Yeah. So you have all these E2 nodes. So this can be a base station or another distributed unit or a CU, which is basically providing aggregate measurements periodically through this E2 related function, dump them into the shared data layer. The XUp reads all that stuff and then puts it back. So now you can drive all sorts of allocation of resources. You're also, I mean, the nice thing about the shared data layer is that, this is kind of common across multiple other functions that you can have in this service management and orchestration framework. So you might have other XUps that will use this. So one thing we did recently, and probably I'll share some demo video next week because we still have an embargo, but the idea of one of the use cases we were testing here is like, okay, I take the aggregate traffic volume over a period, at the level of multiple cells. I do forecasting on those with this forecasting engine, nothing that I presented here. So this kind of evolution of, some of the stuff that we started from. And then I have the forecast. So what do I do with those forecasts? So we said, well, let's feed this into a load balancing engine, which basically allows me to understand how much relative processing capacity I need at different centralized units or CUs. And then I bring this information back to CU user plane, and that gets updated periodically. Yeah? So at the end of the day, what do you do? So you have basically this ability to kind of allocate processing capacity in real time, ahead of time, which to some extent allows you to do all sorts of things. So on the one hand, you don't keep all the resources running when you don't need it. So that translates into some reduction in capital expenditure, some reductions in energy consumption. So you're already running infrastructure in a much more cost-effective way. And then because you're having this tight control, you never under provision, which means your customers will not be unhappy, and then you increase quality of service. So by extension, you somehow mitigate customer churn. So that's all I had. Obviously, lots of credits to a big team behind this. Some of my students or former students, some of them approaching graduation, some of them part-time with NetAI, others full-time with NetAI. And yeah, with that, I'm keen to take questions and see what you think about this.
Thanks, Paul. Questions? While people are thinking of questions, maybe I can ask one.
Yeah.
In terms of the performance metrics that you use, is mean absolute error and things like that still the most appropriate performance metric? Because if I look at your applications such as capacity planning, it probably if I overestimate the traffic, that's probably still okay because I'm able to cope with a lesser amount of traffic. But if you underestimate,
it's a spot on question. I mean, it's still relevant because in the end, you want to make predictions that are, maybe I can pull a plot. So what we do now, actually, we train, I just kind of skimmed over. We said, oh, we train with a cross entropy function because this showed that, performance is better. So now actually most recently, we started using this kind of a capacity aware function, a loss function, which means basically every time I know there is a fixed penalty for underestimating. And that it doesn't really matter if I provide you 1 megabit less than what I told you I'm going to give you or 100 megabit less. I'm still going to pay a fixed penalty for every event, right? So there's a fixed cost. So if you want, the loss function is like, it's a flat line up to a point, then it goes up to 0. And then every time I overestimate, I pay a cost over overestimation. So you can still think about this like having a sort of a linear increase function. So the loss will grow with the amount of capacity I over provision. There is a challenge now because I have this kind of inflection point. So my loss function is not differentiable anymore. So what we did, we kind of introduced a sort of a small slope there. So I don't jump straight to 0, but I kind of have a very slow decrease in between those two steps with like a flat up to that point, and then I go linear. So the idea there is that whenever you forecast, if you slightly over provision, but not hugely, that's fine. What you don't want is you don't want to have underestimation. So you want to have that error staying positive as much as you can. So that's what basically that loss function does. So I try to make sure that wherever I make a mistake, that mistake is like just overestimating. So then I don't have all these kind of SLA violations.
Nice.
But it's super up technical question, and it's funny because you speak with practitioners at times, and they know this underestimation is a problem, but it's hard for them to articulate, like to the point of like, hey, can we just kind of have an offset, making sure that we're always, over provisioning? It doesn't really matter. I said, yeah, but you're missing an opportunity here.
Yeah.
Because you can over provisioning just enough to keep your customers happy instead of like throwing resources at customers when they don't really need them. So some degree of evangelizing involved there as well. So, but yeah, very, very good question.
There's a question in the chat that says traffic can be predicted because if traffic can be predicted probably because it has some fixed pattern or a slow changing pattern. Otherwise, it should not be predictable, right?
Partially right. So some of the parts you saw that actually we can predict. I mean, I showed stuff that what happens over a span of a couple of days. So we do two things here. So we do training with a capacity aware function, but we also do forecasting that is uncertainty aware. So the idea there is basically you use this notion of Monte Carlo dropouts. It's almost like building a Bayesian model where you don't really predict a single time series as the output. You predict the confidence band. So now I know with 95% certainty that my output will be in a range. And that range should absorb all this variability that is, notoriously hard to anticipate. Of course, that's something that you do. I mean, basically, you have multiple passes during training, and you basically have all these dropouts that allows you to do that. It takes more time to get to that, but it does provide you this additional information. So, and this makes a lot of sense from a practical perspective, because let's say there is a service that it's an enterprise customer, and you can't really under provision, although you have a function that always kind of provisions a bit more. You want to make sure that you never make those mistakes. So if you know that, the service will lie in a certain range, you say, hey, I really want to make sure I don't make mistakes here. and I will drive allocation of resources with information that I have at the top end of the band. Whereas if it's a service that I don't really monetize, nobody really plays for cloud gaming yet. I mean, nobody has understood how to kind of monetize that. And the end user doesn't really want to pay because they pay for a subscription. The game provider doesn't really pay the mobile operator for the infrastructure. So then the operator say, well, yeah, this is not a critical service. I don't make money. So I say, I have a budget in terms of how much capacity I can allocate. So I'm going to play with the lower end of the band, for instance. I mean, that's something we don't have full visibility into just yet, but it's kind of common sense in my mind. So
Yes.
One quick question. Oh, sorry. I think you were about to talk.
Yeah.
I jump over. Please go.
Well, let me utilize my seniority and advisorship to preempt Ignacio. But thank you, Paul, for another very nice talk. I remember, still remember your PhD defense talk a dozen years ago in Leganés, and you gave a talk about control theoretic methods, and now you're such an expert in machine learning, so it's nice to hear. And so I have actually two very kind of simple questions, mostly clarifications. Yeah. First, about the Hungarian algorithm. So how does the grid placed on the point cloud, and how do you map like points to the grid vertices? What kind of techniques are used?
Yes, I mean, that's what the algorithm does. So basically, it's kind of I think it's kind of a heuristic that I think runs in n log n time. So basically, you kind of you scan different locations, and then you try to basically find how to move, which points to move on to the kind of the nearest point on the grid.
But I think there should be the first stage, right? Where you place the grid in the first place. There should be also kind of some kind of error minimization, right?
Well, it does.
Yeah,
I mean, I guess you can deploy. If you want, you can build a sort of the mass of the infrastructure, right? So you can think every point has the same weight, and then you see what's the center of mass. Then you center a grid at that point. I think that's one approach to do it. Probably that's how we do it. I mean, in the end, so let's say even if you didn't overlap, what you want to make sure, because in the end the question here is, you want to make sure that the relationship between different points in the original deployments are maintained as much as possible. If you displace everything, let's say with the same constant, let's say on a grid that is, I mean, hypothesizing here, like 1 kilometer away, it really doesn't matter if that's a constant by which, I mean, it's a fixed operation. It doesn't really impact the correlation between the original points. So you want to make sure that those relationships between the original points are preserved as much as possible.
Okay, and another one. Well, probably I haven't listened to the talk very carefully. But you mentioned this similarity with videos, and then you reported the results in terms of PSNR and SSIM, which are kind of classical video quality metrics. So I'm just wondering, what about something else? Like in video streaming, they use now VMAF and some other metrics. So are they applicable, or it just is analogy can just be extended as much?
So in my mind, basically, because if you look at it, so the analogy we draw was basically the intensity of a pixel versus the volume of traffic at one location. And let's say if you have services, you can think about different services as being different channels in an image, like RGB, right? So for us, there was a quality of the reconstruction of the image. It was not really like, you have a bunch of other things that happen in video streaming, like bitrate changing and all that kind of stuff, which is probably a bit irrelevant to us.
Yes, true. I think the VMAF in particular tried to kind of incorporate subjective perception of it. So it's, I think, yes, for you, it's not important, or it's not even relevant.
It's not.
Okay, thank you.
Thanks for the kind words at the beginning. I'm by no means a machine learning expert. I say this sometimes to colleagues here who are, machine learning experts. I'm not a purist, but I've grown to become a good user of ML for the problems I care about. So I think there's loads more people who know more about machine learning than I do. So.
Well, it's all, I think 12 years ago, everybody was at least here on the same plane. So it's nice that some people made an effort to make the transition and make contributions.
Thank you.
Well, thanks for the co-presentation. Just a quick question related to some of the earlier ones. Is there a point in which an increase in accuracy does not have an economic payoff from the point of view of the clients you work with?
Well, yeah, I guess if you don't underestimate, probably not. If you overestimate, we looked a little bit at, for instance, a setting where you translate over provisioning into CPU time. And then more importantly, we looked at, let's say you want to understand how much capacity you need. So how do you allocate more capacity? You need to allocate more resource blocks. So you need more spectrum. Spectrum is expensive. So, I mean, I don't know how much money they pay for, licensing spectrum these days, but as soon as you overestimate, you need to kind of do probably frequency reuse, kick in a bunch of other algorithms. So it's extra operational work. I wish I had a definite answer, but yeah, it's almost like how long is a piece of string?
I guess
otherwise, I mean, you can look.
Yeah, sorry, go ahead and finish, Paul.
So the other thing like that you can measure is, for instance, let's say you know how much memory and CPU time you need for a network function, and then you can look at how cloud provider price that. So every time you kind of estimate and you think you need more memory and more CPU time, there's a unit cost for that.
Mm-hmm.
So you can translate that for different cloud providers.
Yeah, I would be quite curious to see a metric of return on accuracy. How much do you get for every extra little bit of accuracy that you manage to obtain?
Okay.
Yeah, I mean that's the scope of.
That also
pilot,
connects with the question that John has. Is talking about: do you really want such accurate machine learning models?
Yeah, I mean,
what about the energy and sustainability costs?
Yeah. John has a spot-on question. Actually, this is something I mentioned in the talk at Connect. So, I mean, at the end of the day, you don't want to build, a big model like all these natural language models, which have like billions of parameters. And, I don't know, like for the current largest model, it takes, if you had only one GPU, you would need about a year to train it. So then what do? You distribute the training across multiple machines with multiple GPUs, but you keep them on, right? So you don't really save any cost, you just save time. So the question then is, how big should the model be? And actually, I mentioned this briefly, like with the deformable CNN, you have all this accuracy, but it takes quite a bit of time to train. So then there are use cases where, you can use a simple, and we looked at it, you can use a simple model that is much quicker to train and then compromises some degree of accuracy, because now I'm, let's say I'm doing allocation on an hourly basis at the level of a core data center. So I don't really care that much about being extremely accurate. But then if it's something close to the edge and I need to make very accurate inference to, let's say, support autonomous vehicles or whatever, then what I can do, maybe I can have a stripped down version of the model and employ some model compression tools, which will allow me to kind of, have a smaller model that I can train much faster. And I can also have faster inference and even run it on a kind of an embedded GPU. So all valid points. I mean, And I think the operators care about this quite deeply now. Everybody's trying to reduce the infrastructure carbon footprint. So they said, okay, look, let's deploy less and like let's use AI now to kind of power down some of the infrastructure. Fine, but now you move the cost from keeping stuff running all the time into like training neural networks. So it's a very pertinent practical question.
Mm-hmm. Now we are over time, but there are two questions which I think are kind of related when maybe you want to answer them together. One is, based on the predicted traffic, how exactly do you calculate the exact required resources to meet the user SLA? And I'm guessing that's out of scope, or that's whatever the network operator wants to do, or is that?
Yeah. So in that last example I mentioned with ORAN, we use this. There is a notion of relative capacity, which is it's kind of an abstract unit that has been defined by ETSI in some document. I mean, just remember, we don't run a network. So we basically provide this, standardized mention of how much capacity you need, and then different vendors will interpret that in different ways. So they will just take that and translate with whatever is kind of technology specific. But there are sort of standardized general definitions of, let's say resources, if you want. And I think ORAN works with the same notion as defined by ETSI.
Yeah. And then I guess finally, what happens if you have malicious applications that perform attacks? Because if they use a completely different pattern than what are you robust against that?
That's a very good question as well. And actually, we're working on that.
Okay.
It's the first time I had to write to a PC chair to say, hey, look, I mean, we had a paper at using security, which had 5 reviews, all except with major revisions or shepherding, and then we rebutted, and then one of them killed the paper. So the paper was rejected. But I mean, the question there is like, you have to think about, first of all, what's the threat scenario, right? So for instance, if you have a slice network, maybe I don't want to pay for let's say a premium service, but then I can become a bit of a weasel and try to shape my traffic so that it looks like this is some very fancy, autonomous vehicle traffic that has to be served in a certain way. And I want that classifier to be fooled. So, I mean, this is a big problem in machine learning right now. How do you deal with basically adversarial perturbations that try to fool classifiers?
Yeah.
What I can tell you right now, I mean, in the end, we'll still publish this work, but we're working on a tool which is super neat because it's not domain specific. So it works on images, it works on network traffic, it works on voice commands. And it's like a pre-processing box. So you put it in front of the classifier. So you don't really care what the classifier does. You basically purify that input. So whatever adversarial, you're trying to learn what are the robust features in the input and discard those that are not, and let the classifier do its job as if nothing really happened.
Okay, that's pretty cool. I guess final question, is your model interpretable, and how that relates to the cost of the model itself?
Yeah, so we have some idea of like what, how the model reasons about the input. Again, there's some new line of work we're doing where basically we're trying to understand exactly what part of the network acts how when an input looks in a certain way. Yeah, so some of it is kind of, collective knowledge that this kind of works, and then some domain knowledge, and, yeah, it's fine, but there is no like hard explainability applied to them. I mean, you can look at, we looked at tools like TSNE and things like that. It's just to understand like how the model sort of reasons about an output, but it's still, I wouldn't dare to call that, proper interpretability. It's kind of, having a rough idea of what's happening.
Yeah, very cool. Okay, so we are a few minutes past, but really interesting stuff. So thank you, Paul.
Well, thanks for the invitation again, and for all the good questions. Yeah, it's a all a bit of a way to go. Totally. Yeah. Thanks, John.
Yes. Okay. Thanks, everyone.
Cool. Thank you very much, Paul. Bye,
All
everybody.
right, guys. Have a
Bye.
nice weekend, and
Yeah.
see you soon.
See you. Bye.
Bye bye.